Welcome to this video on the electric potential. If you didn't watch the previous video and video 4, you might want to go back and take a look at that just to make sure that you know what's going on because a lot of that information lays the groundwork. All right, at the end of the last video, I asked you to answer this question. So if I had a source charge that was positive, remember source charges affect the space around them and make electric fields. So I'm drawing the electric field in here. We're going to be taking a look at how to draw that better in some subsequent videos. But for right now, what I said to you was that anywhere along any equivalent radial surface, right? Because remember, this is a surface area, that anywhere along around that surface, at that location, there's nothing there, but at that location, we could describe the amount of electric potential that that place has as 1 over 4 pi epsilon naught times q, the source charge, over r, the distance between those two. And anywhere on that same radius, I would have the same electric potential. Now what that's describing, remember, is that if I were to place a charged object at that place, a little test charge, this is how many joules per coulomb of charge that I would place there. So if I place more coulombs of charge there, or an object that had a higher charge, it would have more energy at that location. And this was the equation. We then reviewed that the electric field could also be calculated over there, and it looked very, very similar, but it was actually a different equation, which was 1 over 4 pi epsilon naught times q over r squared. And what I asked you was, can you figure out that using this equation, if I actually did place a little test charge there, how would I account for that using this equation? And so that's what I'm going to start the video off with now. So if we think about moving this little positive test charge, right, from here to this location, right, it would naturally go that way because it's a positive test charge. It naturally moves away from the positive. So we would say that the electric field is doing work on that charge. It doesn't require external work to move that way. Now, obviously, to move it back, it would take external work. So the amount of potential energy that this little charge has relative to its position from this is also equal to, so I'm going to go ahead and write this in here, the amount of electric potential energy that that configuration has is equal to the amount of work that was done by the field, in this case, to move it there. Because we already know that work is the transfer of energy. So we could even show that the change in the energy of the object equals the amount of work done. So that's what I'm going to go ahead and show you now, is how we can actually calculate that. So we've done this now several times. It's super important. We said that work is equal to the electrostatic force times the displacement. Now I'm going to change this to be r, because that's this distance that I described over here. And I really showed that the electrostatic force, which is the force that the field pushes with, is equal to the charge times the field strength times r. Now, I know that the electrostatic field equation, right, is this. And so I'm going to plug it in for E over here. And I'm going to leave that as Q times 1 over 4 pi epsilon naught times Q over R squared. So that's all this. And then I have to multiply it by R. Now I can see here everything's kind of jumbled. I'm going to pull the constant out front here. 1 over 4 pi epsilon naught times little q times big Q over, and this would simplify down to just R. So I see that the amount of work required to move this little test charge from the surface all the way to this designated point would be equal to this. And so that results in the amount of electric potential energy at that point over there. Now we see that it's very similar to this electric potential equation. It's really the electric potential times the charge value that we put on it, and the charge value was this right here. So we see that Q over R, right, this 1 over 4 pi epsilon naught Q over R, that describes the electric potential. So in essence, what I could write is that the electric potential energy is equal to the electric potential times the test charge. And so I can see here that Q times V is equal to the actual amount of energy in joules that would be had. So if you need to watch that again, because it does take you through quite a few steps, that might be helpful for you. But if we kind of go back through this process again, we can see here that there's a lot of kind of inherent information. And here's where I'm going to stop to show you that. So if I stop right here and I see Q times E times R, I can look at this and say, well, E times R, right, E times R left me with V. And so what this could be rewritten as is Q times V. And so we can see that electric potential can really give us a lot of information about how much work is required to move. Now, a very important idea that we need to really drill into our minds is that electric potential means nothing unless I have a relative location of which to measure it. So here's an example using gravity. Say here is the floor of a second-story building right here. So this is the second floor of the building. Here's the first floor or the ground floor. And I place a table up here, and then I place a ball on the table. Now, the ball has zero potential energy due to the tabletop. It has X amount of potential energy due to the height of the second floor, and it has X amount of potential energy due to all the way down to the first floor. So you can see that the amount of potential energy is always relative to some place that we consider to be zero. We could consider the table to be zero. We could consider the floor to be zero, the second floor. We then could consider the first floor to be zero. And so really what we're doing is we're showing what the difference is in those locations. Now, if I got rid of the ball and I just described the locations, I might say that's a point, this is a point, and this is a point, right? And each of those locations might describe the gravitational potential, right? That's just describing the number of joules per kilogram of mass that I could have if I put an actual mass at those locations. So we can see that it's really what would have to be said would be that the gravitational potential here is zero, and therefore this is not zero, and therefore that's not zero, right? And so we would use something that we would refer to as the delta V, the difference in potential, in order to actually give a value that made sense. So if we look at this scenario over here, the actual charge itself and the little location close to it would be considered the place of highest potential according to this equation. When R is small, V is very large, and as R gets larger, V gets smaller. So we can see that that makes sense. So when we're describing the amount of work that needs to be done to move a charge in a field, it's actually not good enough to say Q times V. It's rather better to say Q times delta V, because it's assuming that somewhere you start is zero, and then you move outwards. And so we can work our way through this equation and see that the amount of electric potential energy, or the amount of work done, is equal to Q times delta V, but it's also equal to Q times E times R. And so there's lots of variations that work can equal. And so it's very important to be able to structure your thinking to understand how this might work. Now, the last term I'm going to leave you with in this video is just a name that we give to these lines where the potential is the same anywhere on this radius. So I could draw another one over here, and you can think about there being an infinite number, right? We call this a line of equipotential. Equipotential means that there's equal potential all the way on that line. and so there would not be the same amount of potential on this closer line to this further away line because of the equation. Now, one thing I will tell you is that electric field lines, E, are always perpendicular to equipotential lines, which I'm going to draw just like this. So if you know that that's true, that electric field lines always point perpendicular or always cross perpendicular to equipotential lines, that if you know the equipotential lines, you might be able to draw a field map. So what I would like you to do is think about what that would look like, and the challenge is, can you draw a field map for a scenario that looks like this by drawing some equipotential lines on first and then some field lines. In the next video, we'll take a look at that.